Hello everyone, this is Sally Ward-Foxton with the E-Times. You're listening to our AI podcast, AI with Sally. This episode is sponsored by Arteris. AI is changing the economics of cybersecurity. The same AI systems that can write code and analyze software are increasingly capable of finding and exploiting vulnerabilities, much faster than people can do it, at much bigger scale and at a fraction of the cost of traditional hacking. So what happens when those capabilities move from software into hardware? A chip can be functionally correct and still leak sensitive information, and unlike software, it's very difficult or impossible to patch hardware once it's been deployed. My guest today is Andreas Kuehlmann, General Manager of Arteris Security. He's an expert in hardware security. He's going to tell us why we need to consider security earlier in the design process and give us some hints on how to build more secure chips. Here's my full conversation with Andreas. Okay, hello Andreas and welcome to the show.
Hello Sally, thanks for having me.
So I think probably everyone listening to this heard on the news in the last few weeks about this event or this incident at OpenAI where the AI model was practicing hacking and basically it's escaped its sandbox, which sounds very, very frightening, and actually done a real attack over at Hugging Face. We're going to talk a little bit more about AI and hacking and AI and security today, but maybe you can kick us off by talking a little bit about, how did we end up with using AI to hack systems in the first place? Why are we doing this? And why is it mainly a software problem so far?
Yeah, I think I'm surprised that people are surprised, right?
Okay.
Over the last, couple of years, we really saw that the LLMs got pretty good in helping coding, software coding, right? So meaning they understand software, they understand source code. And it was just a question of time that they also understand vulnerabilities in the source code and can exploit them, right, to essentially hack other systems. But it's not only the understanding of the source code, there's also a lot of public material out there. So think about the CVEs, right, the common vulnerabilities enumerations, the CWEs, the common weakness enumerations. So there's a lot of public information out there that the LLMs can also use. And the LLMs are just very good in simple things like password guessing, right?
Yeah.
And so it's really a combination of all of the above. So I don't think anyone, should be surprised that the systems are getting hacked. Why software first? I think the big difference, versus hardware, right?
Yeah.
Why is not our chips attacked yet, right? And I'm emphasizing yet, right? I think the difference is really, if you look at software, the history of software security is more than 20 years, right? So there's a long history, there's a lot of knowledge on the software side. Secondly, there's a huge amount of open source software. There's probably, several hundreds of millions of packages just in GitHub that are available. And number three, this is being used in commercial software. Right, commercial software today, nobody writes, 1 million lines of code or 10 million lines of code of scratch. You're using a lot of, open source. Today is up to, 98% of the commercial software is using open source, which there are known vulnerability in open source. We don't have that in hardware. So hardware has a very small amount of open source. It's a few hundred packages. And number two, it's really not being used. Most commercial chips are really, used with internal development or, third-party IP providers. So not there yet, but I think it's a question of time, right? Yeah. That the AIs, get better and better in hardware hacking.
If we can use AI to scale up hacking efforts, we're going to basically change the economics of it a little bit. How do we change the economics, and why is this so frightening?
I think what AI really does, besides being able to combine many pieces of knowledge that when you're a human being you have to do this manually, it drastically reduces the cost, it drastically increases the scale and the automation, right? An AI can essentially start hundreds or thousands or millions of attacks in parallel. It can combine, various weaknesses and vulnerabilities in our systems, right? And it's very cheap, right? So it doesn't cost a lot of tokens, right, to essentially, generate an attack. And it is concerning. It is concerning, when the models start really, getting so mature that, we have to really be more careful.
I know you said that software has a lot of known vulnerabilities, especially if we're using open source software, but hardware is kind of different, as you said. There isn't much open source kind of hardware available. So traditionally, I guess to attack hardware, to find hardware vulnerabilities, you needed to have some expertise in chip architecture, microarchitectures. You needed to understand low-level programming. If I can use AI to basically do that for me, does it make it easier for all different kinds of entities to try and start hacking now on hardware?
Oh, right on, right. I mean, till Spectre meltdown, which was really, uncovered in 2018, we all believed the chips are secure. But we were in this fantasy, oh, it's only the software the problem, the hardware is not a problem. And that really changed dramatically, in this discovery of Spectre and meltdown. And there's not, you have regularly new versions of Spectre, regularly new versions of any attacks, right? But figuring out these attacks, finding those vulnerabilities is very labor intense. And as you mentioned, it really crosses boundaries of expertise. But again, they're LLMs very good, right? LLMs can essentially, stitch together different domain knowledges. And again, LLMs can take research that is very tedious, right? Automate that and massively let's try this. And that's an example, actually, fairly recently, outcome of a university research system called Eugen. They were actually able to automatically generate, Spectre version 1, so the very old Spectre, but generating it automatically in a few minutes in an AI system. So
Wow.
again, right, I think it's a question of time that I think people see hardware attacks or, hardware attacks or hardware vulnerabilities being part of larger attacks that are stitched together.
If we kind of worst case scenario, if we get to the point where AI makes hardware significantly easier to hack, the consequences are quite different as well as they are for software, right?
Yeah, I mean, so if we see attacks in the future, it's probably going to be a combination of, social engineering, software vulnerabilities, hardware vulnerabilities. I mean, they get very sophisticated. But to your point, the cost of a vulnerability in hardware versus software is very different. In software, at least, if you have a web application or so, you can patch it fairly quickly, right? I mean, even if you have on a device and it's maybe more complicated, right? In hardware, very often you cannot fix it at all. You don't want to really, maybe you have to, disable some functionality. Maybe you can update it in the firmware, right? Maybe, you can lower the performance, right? But the cost structure of mitigating a hardware vulnerability is very different than it is in software.
What if I had a chip that I designed earlier before AI hacking was a thing and it's still out there kind of in an edge device somewhere? Because hardware kind of stays in the market for years and years. I think this is
Right on.
particularly scary. Yeah.
No, it is. I mean, you look at boxes. We ship these boxes. The chips are in there for 10 years, 20 years. Cars, this is for a long time. You're absolutely right. This is not only about chips that we design today, manufacture today, and put in products today. It's about all the legacy. By the way, this was the same with software, right? When essentially, a lot of embedded devices suddenly got connected on the internet. The software was never really designed for security or developed for security, but suddenly they're connected on the internet, so they became vulnerable, right, for attacks. So we had seen that movie in the software world before, and now it's just expanded to the hardware world.
If I was designing a chip today and I kind of want it to be AI proof or AI secure, I mean, is that part of the verification flow today? Or if I'm doing verification as I would and I get the right answer, I verified my chip and it all works. That doesn't necessarily mean that I am AI proof, right?
Yeah, I think there's, insecure, unfortunately, there's never 100% secure.
Okay, just more secure. Yeah.
But there are best practices, right? There are best practices in software security. There are best practices in hardware security. And I think the big difference, a lot of people mix up functional testing or functional verification with security verification. Functional verification, essentially what it does, yes, the chip does actually what the chip is supposed to do, right? If it's a CPU, 1 + 1 is indeed 2, right? But that does not necessarily mean that the chip doesn't do something that it shouldn't do, like a security vulnerability or leaking out some data, or having a side channel where one process can snoop in another process and extract data. So the two things we call functional testing, really positive testing. Again, right? Does the chip do what it's supposed to do? And security testing we call negative testing. Is it not doing something that we didn't write about, right? We didn't want it to do, right? And it's actually what's so interesting, Sally, is what we see very often. It's a mindset, because you look at and that's the same in software, right? Software testing, hardware verification. You see the QA organization or the DB organization. Their mindset is, my job is to make sure the system does what it does, versus thinking about what it could do that is a security vulnerability is a mindset shift. And sometimes that's a challenge in organizations that are really trained, on the functional testing, functional verification side.
If I was working within a verification flow or a tool chain that I already have, does functional verification have testing in it for issues like security like this?
People do, right?
Okay.
But I think this is an area that is evolving. That's an area that is maturing. I mean, as I mentioned, really the whole hardware security issue is fairly new, right? 2018, big wake-up call. And you may remember, that was all over the news. Intel, AMD, ARM, what the heck?
Right. I mean, I'm laughing, but it wasn't funny. Yeah.
It was not funny, right? So the whole notion of we are not only doing functional verification, we also need to do security verification is on everybody's mind, for the last years. And what we see is it's not only, that people are, I don't want to be in the front page of the Wall Street Journal. It's also, we see increasing number of regulations, of standards that are really forcing the chip industry to make sure you have best of state of the art security testing. An example, for example, is ISO 21434 standard. That's an automotive standard, and what this is saying is that every chip that goes in a car needs to be certified for cybersecurity. So that puts now a burden on the chip development organization, not only doing functional verification, but also doing security verification. So it's a journey. I'm always like, security is a journey, right? It's not like, oh, you buy some technology, you flip a switch, and suddenly everything is done, right? It's a journey, over multiple years, over multiple generations of chip development, and people learn, as they go forward.
If I let's say I'm making an SoC and I'm buying blocks of IP from different vendors, or maybe I'm buying chiplets even from different vendors, and I'm somehow stitching them together, who's really responsible for the security implications of the interactions between those blocks or between those chiplets?
Very good question, Sally. I mean, fundamentally, from a technology point of view, security is not composable.
Okay.
So what that means, if I have a system of 3 components and I make sure the 3 components are secure, that does not mean that the composition is secure, right?
Okay.
But going back to who's responsible, right? I mean, take the European Cyber Resilience Act, right? That's actually going to be, there's a first phase starting in this September, and it's going to be fully enforced next year. That makes any electronic product provider liable for any security issues through the life cycle of the product. Is actually a very strong legislation. Now, if you're a provider of whatever box, right, and you compose the box of many different chips from different providers, the chips themselves have IP components, maybe they're chiplets from different providers, you ultimately are responsible. But what that means is you got to go down the supply chain and essentially make sure that the supply chain, your IP providers, hey, what have you done for security? Can you show me and demonstrate to me that you did the best practice in terms of security assurance, right? And then when you compose the system, you have to still verify that in its entire composition. It's a very good question. It's a very good economical question in terms of who ultimately is responsible and then potentially liable.
But can I test, or how do I test for vulnerabilities, for hardware vulnerabilities, while I'm doing the chip design process? What What's best practice really for doing security verification like this?
Yeah. Yeah, what we learned in functional verification over the last 30 years, I mean, there's this term shift left.
Yeah.
Shift left mean start as early as possible, right? Don't start functional verification, when you're ready to tape out the chip. That's exactly the same thing in security, right? Start early, meaning when you start designing the architecture, when you think about the functional spec, at the same time develop your security spec. And the security spec, boils down to security requirements, and security requirements come from your use case, come from your customers, come from your applications, right? So, what are you worried about? What's your threat model? And then what specifically the methodology that we recommend is we call this the asset-based methodology. Asset means what are the assets in your system that you worry about? Could be an encryption key, could be some secret data, could be, in a weapon system, right? The target coordinates, right? Could be, could be anything you really worry about. Could be, a register on a chip. It could be a memory range, or it could be some other entities. And then start from there and then essentially figure out what do you worry about? How do you protect that? And how do you verify that's indeed protected? I mean, this negative testing aspect that I talked about before, right? So there's a methodology for that, as we just spoke, right? Start as early as possible. I mean, don't wait too long, and then essentially have a big surprise, a week before tape out.
Is there a specific way that we can test for the interactions between different blocks? I know this is where security vulnerabilities sometimes crop up, but is there a specific way we can test those interactions and make sure we're as secure as we can be?
Yeah, so what we recommend, right, is that you start really on the block level.
Okay.
You on the block level, I mean, could be an IP block, could be block that you internally develop. And you essentially, specify the security requirements. You verify the security requirements with, whatever technology, right? We have some technology, there's other technology out there to verify that. Once you have the block verified, you repeat that verification when you start composing blocks to subsystems. And then when you put the whole system together, when you put the firmware, on the system. So firmware, for example, is a big exposure, right? Very often you have security components of a chip that are highly configurable. Could be configurable in hardware, could be configurable in software and firmware. So making sure that the firmware actually configures these components correctly is very important, right? Because they could all function, in all the particular configurations, right? I mean, they work exactly as specified, but then you misconfigure them in the context, right? I mean, it could be vulnerability.
Could I use AI as part of this process? What if I use AI to kind of attack my design or the RTL for my design so that I can try and find out if I've got vulnerabilities?
100%. In fact, as you see this in the software world right now, right? There's a set, what AI really does, these, latest frontier models with all their cyber capabilities, they're disrupting the entire application security industry, because there's yes, I mean, we are all scared about the offensive use, right? But they can equally use them defensively, meaning finding out proactively, is there anything I should worry about? And these LLMs are getting better and better. I mean, we all know this, right? I mean, every half year there's an upgrade. I mean, they're just amazing how fast they evolve, right? It's absolutely the direction to go. In software, we see this already. I expect the same thing as, the hardware, the AIs get more mature on hardware security. I expect the same thing.
All right, tell us a bit about where Arteris fits in here, how you can help. Particularly, I know you have this Security Radix product. Tell us a little bit about what that does.
Yeah, I mean, I talked earlier, right? Security is the journey,
Yeah.
right? And the journey means, it starts really, from something where organizations sometimes don't know a lot about security. Sometimes they're very immature, but we help, our customers on that journey. In essence, build a security program. And that's always about, people, processes, technology, right? People meaning, we offer training. How do you think about security? How do you prioritize security? Where should you apply security in your process, right? Then the process itself, we have a particular methodology. I mentioned the asset-based approach. That is something we have very much refined, and there's a really good process in place where we train our customers on. And what's coming out of that methodology is really, here are the security requirements. Here is how you can encode them in a way that are actually verifiable. Verifiable mean you can give it to a tool. The tool comes back with a yes, no answer. Yes, it passes. No, it doesn't pass, right? And then you have technology, the radix, the security radix technology that you mentioned is actually, doing what I just said. Is essentially taking these requirements and then verifying them on the real chip. What we use in radix is a technology that's called information flow. So think about what we do on a chip. When we have the assets, we tag these assets, and then we track where the information of these assets goes through the chip. So if there's an encryption key, we can exactly see where the encryption key goes. And as such, we can see where it should not go, right? There could be then, a rule that's essentially saying, do not leave this boundary of the subsystem. And if the key leaves the boundary, red flag, you got to go back in and do some mitigation. What's so interesting about the technology is, of course, ultimately it's a verification technology. But in the beginning of the process, it's also being used as a design tool because we can show the designers and the architect where these assets go. So it's for them kind of, oh yeah, that's what I meant to do. It stopped exactly here where I have, some boundary defined. And it doesn't go over there, but maybe it goes somewhere which may not be a violation, but it could be a surprise. So it's a very helpful product in the beginning when you actually define the security requirements before you go into, what we call regression testing, meaning you run it every day. You change your design on Thursday evening, you made a mistake on Friday morning, said that this requirement doesn't pass anymore. You got to go back and fix it. We call this the guardrails, right? You have some guardrails, so you're not falling off the, whatever bridge, right? When you design your chip.
Okay, what is driving this need for security verification in particular? You mentioned regulation before, but is it mainly regulation, or is this new real threat, right?
I think all of the above, right? I think people are aware of, they see what's going in the software world, right? And a whole number of our customers, even if their customers are not asking yet, right, they're getting proactive, right? Because chip development cycles are multiple years. You cannot, this is very different than software. You cannot start, oh, wow, we have a problem. And as you mentioned earlier, chips are in boxes for a long time, right? So we see a number of our customers getting proactive. But the big drivers are, certifications, standards, regulations. We see a very, very strong interest in the European Cyber Resilience Act that I mentioned before. It's becoming active, and it makes companies liable. Meaning, if there is, an incident and you cannot demonstrate, that you had a really best practice in security assurance, this can be very, very costly, right? And so we see that the main driver, automotive, I mentioned earlier. There are other areas, where people start standardizing and start essentially requiring, think about security not as an afterthought, think about security right as you develop the chip.
Can you tell us anything about what kind of customers you work with, or who needs your help?
Yeah, no, it's a good question. The simple answer is everybody.
Okay.
Everybody makes a chip, right?
Yeah.
The pure semiconductor companies, that's their business model. Their companies, system houses, look at hyperscalers. So they do, chip development for their data centers or for other purposes, right? There are third-party IP providers, that essentially provide the blocks that we talked about earlier. That need to be secured. So it's really anyone, who develops chip. I can give you one specific example because we just had a press release that is ARM. So we have been working with ARM for a number of years on really these advanced, side channel vulnerabilities. We just announced that ARM is expanding the usage of the radix technology, to really make sure, that the chips are indeed secure.
Great news. Any last words of advice for people listening to this that are suddenly worried? What should they do?
I think get going.
Okay.
I mean, it's very simple, right? It's like, I know it's always, everybody is oversubscribed. Everybody needs to get the tape out tomorrow, right? And if not tomorrow, the day after tomorrow. And everybody feels later, later, later. But as you said earlier, chip development cycles are very long. Building a security program is not just overnight. I mean, there's people involved, there's organizations involved, there's technology involved. Get going. And we have a number of customers that for a number of years now started really seeing that and started building the security program over the years and are very far ahead. I mean, very, very, very good to see, right, that organizations are adapting that. So my last word is, get going.
Get started. That's great advice. Thank you so much, Andreas, and thanks for coming on the show.
No, thank you, Sally. Really, really, really enjoyed the show. And
thank you, Andreas, for joining us, and thank you, Arteris, for sponsoring us. If you want to learn more about Arteris, check out the links on the podcast page at eetimes.com. Thank you for listening.